All right, kids. So this is going to be the next in our series of lectures where we will be discussing recurrent neural networks. First, before we begin, I'd like to show you a little bit of code derived from an open source project. So take a look at this code. Can any of you guess which project this came from? Anyone? Someone want to take a guess?
Programming, some C++ contest or something.
It looks like Linux code, right? And observe something very interesting. So this is writing a little function. It's in C. Everything is perfect. Every parenthesis that's opened is closed. Every curly brace is closed. The test, if you look at the if condition, the tests are consistent. If you're looking at this loop, within the loop, you can see that the index being used within the loop is the same as the index for the loop. So it looks like a perfectly good piece of code, right? Same thing. Here's a little bit of math. Now this looks like a Wikipedia page, and it's kind of complex and very mathy looking, but it's convincingly mathematics. It's a lemma. Let C be a set of the construction. Let C be a Gerber covering. Let F be a quasi-coherent sheaves of O modules. There's a lot of very kind of convincing looking math over here, and even a figure which seems to be kind of reasonable, right? And if these things aren't convincing, if you want to know what these things are about, here's a little bit of a Wikipedia page, which should give you an idea of what I've been talking about so far. This is a Wikipedia page about naturalism and decision for the majority of Arab countries. Capital A was grounded by the, it's obviously nonsense, but it again looks very convincing, and it's all fake. Now, all of these, it's all automatically generated text, automatically complete with formatting and LaTeX code for the Wikipedia page with the equations which even cross the figure. And in the case of the C code, it has parentheses being opened, indices being set and incremented. All of these are automatically generated by a neural network. Now, for example, this one over here, this was a neural network that was trained from Linux source code. And what is really
actually, this piece of code has an issue. The index I is not declared.
Pardon me?
Index I is not declared. The
Correct,
variable
right?
is not declared.
But the point is, it looks very complete, right? You don't know that the index I is not a global index outside of this code. Index variable is a global variable outside of this code. Locally within this, it looks convincing. That is the point, right? And this is just a neural network trained on Linux source code. And what we really see is the completeness. It's opening a parenthesis, it's closing it. It's opening a brace. Much later, it's closing it. Within the code loop, it's using the right index. And the memory of this thing is not sharp. So when it opened this subroutine over here, it kept track of all the operations for an arbitrary amount of time until it closed the subroutine. So the thing has structural and semantic consistency. And so this is all of these, whether it's the source code, in this case, this was trained from a bunch of papers on math, I think. The network which produced this was trained from Wikipedia pages. And the interesting thing is that the network, the code for this, you can find this on Andrej Karpathy's page. It's really very simple. It uses very simple architectures. You can download it, or you could. This is more than 5 years old, 6 years old at this point. And 6 years ago, you could generate this kind of sophisticated stuff after training something on your laptop for not a very long amount of time. Of course, the actual state of text generation that uses more sophisticated models and are trained on much more data is actually way better. So this is entirely randomly generated. And if you read it, you're going to see it's very convincing. One of the many sages of the time, the Bodhisattva Sakyamuni, with dates, was a popular religious figure in India and around the world. This Bodhisattva Buddha was said to have passed his life peacefully and joyfully without passion and anger. For over 20 years, he lived as a layman and dedicated himself towards the welfare, prosperity, and welfare of others. Among the many spiritual and philosophical teachings he wrote, three are most important. The first titled The Three Treatises of Avalokiteshvara, the second, The Teachings of the 10 Questions, and the third, The Eightfold Path of Discipline. This entire thing is randomly generated by a neural network, and it's very consistent right down to the Eightfold Path that is relevant to Buddhism. So you can see how powerful these networks can be and how convincing they can be in generating series data. Now, all of these, what's going on here? Now, all of these are examples of modeling. In these examples, we were learning to generate, but more generally, you can learn to analyze, produce, predict, or classify series data where we have many values arranged in a sequence, and the order in which they occur matters. So consider the problem of, say, speech recognition. We have to analyze an entire speech signal or the sequence of feature vectors derived from the speech signal and recognize what was spoken. So the input is a sequence of vectors. The output is a classification result for the entire sequence. Entire sequence, which could be a varying length before you make your prediction. So this is a problem of modeling series data or text analysis. Look at this. The Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed on average 30 points a game and have shown no signs of improving anytime soon. Now, if you're a Pittsburgher, you read this every season. This is what they do. But then nowhere in this little bit is it mentioned what game they are talking about. Are they talking about football? Is it basketball? Is it soccer? Is it baseball? Is it cricket? You don't know, right? So this is a text analysis problem. You have to read the sequence of words and you have to figure out what game it is. And if you're a Pittsburgher, the moment the Steelers are mentioned, this is a football game. So, but the thing is, you have to read the entire sequence of words in the right order before you can take a decision. You can't drop words or you can't read them in random order. So again, this is a series modeling problem. Or same thing with, say, if you're performing machine translation, the input would be a sequence of words in English. The output must be a series of words in French. So again, this is a series modeling problem. Or let's say if you're making predictions about the stock market, you consider the entire sequence of past values and you make a prediction. Your prediction could be, so you'll be reading, maybe you have every day of the week, you collect stock values for a bunch of stocks, stock indices. So you get a vector of values every day. You read them for all the past days. And based on all the past stock values, you make a prediction. Your prediction could be a scalar prediction. Should I invest today or not? Or it could be a vector prediction. Which are all the stocks I should buy today? Now, all of these are classification and prediction problems involving series data, where we consider sequences of input vectors and produce one or more predictions. And what we'll see in the next few lectures is how to do this using neural networks. Now, before I continue, in all of the following slides, I'm going to use a simplified figure to show a neural network. So far, We've seen neural networks as layers of neurons connecting to layers of neurons, like this one. But now imagine seeing the same figure from this side. So now it will look like this figure to the right. This figure here is the same network as the one to the left, except that you're looking at it from this side. So each box over here is a full layer, which is being viewed side on. So this little purple box represents this entire sequence of values. This little green box represents this entire sequence of neurons. This one represents this entire array of neurons. And the arrow over here, these arrows represent a full connection. So when I have an arrow from this box to this box, it means that I have two layers of neurons and the two layers are fully connected. So we're going to use this representation repeatedly through this lecture. So for example, if I have a network of this kind, where I have two layers, in general, I'm going to be representing inputs with blues, hidden layers with greens, and output layers with pink or brown. So this network is something where you're taking two input vectors, and the hidden layer is reading both, and then it's passing them down. When I view it side on, this figure is going to be drawn in this manner, in the manner that you have to the right. Or if we have a network of this kind, this network viewed from the side is going to look like this figure to the right. So anytime you see this kind of figure with little boxes, in your mind, you must interpret this box to represent a layer of neurons. You must interpret every arrow to be a full connection. So now returning to our series modules, consider the stock prediction problem. Stock prices typically follow trends. So if you want to know if it's good to invest today, you want to look at how the stock has been behaving over the past several days. Ideally, you look at the entire history of stock values. But at the least, you at least want to see enough of the history so that you can track the trends. So one simple solution over here is to simply have a net that considers stock values from the past several days as input. So at each day t, is going to consider at each day it's going to consider the stock values on that day, on the previous day, 2 days earlier, and then 3 days earlier, and it will include all of these in making its prediction about whether today is a good day to invest or not. And so each day you would sort of look at the past few inputs and slide forward to make your current prediction. Now, we've already seen networks of this kind. Does anyone remember what this network was? Anyone?
Time delay neural network.
This is just a time delay neural network, right? So we're familiar with this kind of modeling. Now, the network that we just saw is a finite response model. At each time t, it takes as its input the current input and the past n inputs. In our example, n was 3, and it makes its current prediction. So anything that happens at time t, for how many instances will it continue to influence the output? Anyone? In this model, if say n is 4, so it's looking, in order to make a prediction, it's looking at the input today, yesterday, 2 days ago, 3 days ago, and 4 days ago. So if something happens today, for how many days will it continue to influence the prediction?
Next 4 days.
Next 4 days, right? So this is a finite response model. to see again visually why this is a finite response model, say consider some event that happens at time t, capital T, right? As you keep making your predictions left to right, for all predictions on days before t, whatever happened here has no influence on the output. But then as you slide forward, as your predictions slide forward in time, this x of t will continue to influence the output for several steps. It's going to influence the output even here. And then eventually the window of input that's being considered is going to slide past x of t, and it's no longer going to influence the output. And so this, something that occurs today, only affects the output of the network n days into the future, where n is the width of the input window, 4 over here. So the amount of time for which the network responds to any change in the input is finite. So this is a finite response model. Something that happens now influences the output for only a finite amount of time. So now say you want the network to consider longer periods of history. The way to do it is, the trivial thing is to explicitly increase the history considered by the network. What would the problem with using this approach be? Anyone?
Too many weights. Need to
Too
get
many
it.
weights.
Yeah.
Specifically, the further back into time you look, it's going to look for, the number of weights is going to increase. You may think, oh, well, my GPUs are large, my computer's got lots of memory, CPU is fast, this is not a problem. But then the length of time for which you have to look back may be arbitrarily long. Consider the stock market. The stock market has daily trends. It also has weekly trends. So this is the stock market between August of one year and December of the next year. So you're going to see daily trends, you're going to see weekly trends, you're going to see monthly trends, you're going to see seasonal trends, you're even going to see annual trends. So what happens at Thanksgiving this year is going to be pretty predictive of what happens at Thanksgiving next year, but you must also consider everything else that happens in between. So what happens at Christmas here is going to influence what happens. It's going to be somewhat predictive of what happens at Christmas here. The fact that the purchases go up at Christmas time means that 12 months later, around Christmas time, you can expect to see an increase in commerce. So at the same time, the overall level of commerce is going to be governed by everything that happened in between. So, and it may not just be one Christmas, right? The fact that you saw something last Christmas doesn't tell you anything about the fact that you will have more commerce this Christmas. What really tells you that you're going to have more commerce is that you saw a lot of increased commerce the past several Christmases, right? And so that is going to, you're going to have to consider all of that. So again, Tushar, if I just consider only Thanksgiving days, that doesn't tell me the whole story. The entire economy may be down. So you want to say it's going to peak on Thanksgiving, but relative to the rest of the economy, right? And so there's always, you can't just pick and choose. There's a lot happening over here. And so in principle, all of the past influences the market today. Although things that are further past may have less influence than trends from the recent past. And so to consider all of these trends, we want the system to have infinite memory. We want an infinite response system where an event today continues to influence predictions forever into the future, although the influence itself may fall off rapidly with time. So speaking of Thanksgivings, the fact that the sales go up every Thanksgiving over the past 20 years tells you, or the past 10 years, tells you that you can expect increased sales this Thanksgiving. But then the exact amount that was of commerce on Thanksgiving 20 years ago has no relevance to the amount of commerce you expect today. It's the overall trend, right? So you want to have influence forever into the future, but you want it to fall off with time. Now, if you try to build this infinite history model simply by increasing the width of the input window arbitrarily, this is when you'll end up with an impossibly large model with an unbounded number of parameters. What we need instead is a model that has a finite number of parameters, and yet using only a finite number of parameters, it considers the infinite past in making its predictions. So we want a finite sized infinite response model. So is that making sense to you guys? Any questions? No? In that case, we have a poll. 10 seconds, guys. All right, let me stop this. 18 of you are not paying attention. Anyways, please do. So convolutional networks like the time delay neural network are finite response systems, right? If your analysis window goes past your input is no longer going to affect the output. So these are finite response systems. And because of that, an input at any time t is going to only affect the output for as long as the width of the analysis window itself. So in a TDNN, which is a convolutional network, an input at time t will not influence the output for all time. So the second statement is false, the first statement is true. Now, can anybody suggest to me how I can have an infinite response system without blowing up the number of parameters? Anyone?
You can have a feedback loop.
You can have a feedback loop. That's the obvious thing to be doing, right? So a simple way to get an infinite response system is simply to feed the output at any time back as input at the next time. So yt is f of xt, which is the current input, and y of t minus 1, which is the previous output. For this to work, we need to define the initial state at time minus 1, just so that we can make a prediction at time t equals 0. But thereafter, if you consider just a single input at time 0, right? And let's say you have an input at time 0 and no further inputs. The input at time 0 is going to produce an output at time 0, y0. But then subsequently, even though the rest of the x's are 0, y0 goes in here, and so you get y1. Then y1 goes in here, and then you get y2, and so on. And so you're going to have these outputs. These outputs are going to feed back, and you're going to continue obtaining outputs for the rest of time. So basically, a single input at time 0 is going to influence your output forever. When this kind of model is a neural network, and the neural network has this kind of structure where the output feeds back into the input, this is called a NARX network, or nonlinear autoregressive network with exogenous inputs. Nonlinear because the net is nonlinear, autoregressive because it regresses over its own past outputs. Now, in the most generic form of the output at any time t is going to be dependent on all past inputs and all past and present inputs and all past outputs. More practically, you're going to only consider a small number of past inputs and outputs. So this network is actually an infinite response model, even if it just regresses on a single past output. And where is the information about the past stored over here? The information about the past is now stored in the output. So here's how the computation would proceed. At the initial time, you get an input, it's going to produce an output. Then at the next time, this output and the current input are both going to feed into the network, and you produce the next output. And this is going to continue. So at each time, the inputs to the net are the current input, xt, and the previous output, y of t minus 1. So if I want to show the complete set of computations that are performed for an input series, then this is what it's going to look like. This figure shows every computation step. So the input over here and the previous output are fed into the network and processed by these layers. Then the output here and this input are fed back into the network and processed by these layers. Then the output at this time and the next input are going to fed back in, and so on. Now, this figure is slightly awkward in that I'm showing the yellow boxes here are not layers. The yellow boxes here represent the output of the network. So the output layer is in fact these brown boxes. As I mentioned earlier, I'm going to represent output layers by brown boxes and hidden layers by green boxes. The purple is the input, the yellow is the output. So if I were to use a more standard representation, this is going to be the figure. But I just show the output layer. So the output of these brown layers is going back into the first layer at the next time as input. And so this is the actual sequence of computations that happen, right? And you can view this entire structure now as just one large network. I may have drawn it very strangely, but then I could have straightened the whole thing out. And if I straighten it out, it just looks like a very deep network, where this now looks like a hidden layer that feeds into the sky. There's one minor distinction. Every column here is identical because you're using the same network at each time to compute the output. So every column here is identical. Also, there's another difference from the usual nets that we've seen in the past, that these inputs, which are these blue boxes, go in at various positions in the net, not just at the very start, but at various positions in the net. The flow of compute, and also you get an output at various positions in the net. So this is different from your standard MLP. In an MLP, you'd have one input here and one output here, and that was it. Here you have inputs going in at different positions. You have outputs coming out at different positions. The flow of computation, however, remains directed. It just follows the arrows. So now an input at any time influences the output at any time if you can follow a continuous sequence of arrows from that input to that output, from the input to that output. So because there's a continuous sequence of arrows between here and here, this input influences this output. In fact, this single input, as you can see, influences every single output. And now you can see why an input at any point is going to affect the outputs for the entire future. So now, in the previous example, this was a NARX network where the output at any time depended only on prediction at any time depended only on just the immediate previous output. But you can have a more generic structure where at any time you're looking at the current input and a bunch of inputs from the past, and the previous output and a bunch of outputs from the past. So in this example, each prediction is looking at 2 previous outputs and a window of 4 inputs. You can generalize this, and the number of previous outputs and the number of inputs the network considers at each time is going to be the order of the network. So NARX networks are instances of recurrent networks. They're recurrent because the computation in the network at the current time affects future computations. And these have been very popular in time series prediction tasks like weather prediction, stock market prediction, or other phenomena where you have a distinct innovation process that affects the system. Now, the NARX model allows the net to refer to the infinite past in making current predictions, but the memory about the past is encoded in the output of the network at the past times. The memory is not stored anywhere within the network itself. You have to capture the output and you have to feed it back. So the memory about the past is stored outside of the network in the output and not within the network as some state variable. What we want is the network itself to somehow remember the past internally. So what we'll do is to introduce an explicit memory variable whose only job it is to remember. And now we're going to include this memory variable in the computation. And the memory at any time is going to itself be a function of the previous memory, any hidden states of the network, and maybe the output. So this collection is going to somehow give you what the network must remember now. The hidden state is going to be a function of the input and the memory, and the output is a function of the hidden state. So the key piece is that instead of letting the output store the memory, we've introduced an explicit variable which within the network whose job it is to keep track of the memory. So let's see some models that use this structure. This kind of model was in fact introduced in the late 80s, 1980s. And modern recurrent networks are basically an extension of this idea. So let's look at some early models. The first one is the Jordan network. Jordan networks were introduced by Michael Jordan, the same guy who invented latent Dirichlet allocation in this 1986 paper, Serial Order, Parallel Distributed Processing Approach. In Jordan's model, the memory is stored by a memory unit that simply retains a running average of past outputs. So the memory at any time is going to be some new times the memory at the previous time, plus the most recent output. Now, at this memory, at each time, is then fed into the hidden layers for the next time. In Jordan's original model, the input itself was assumed to be fixed. It's called a plan. And the objective is to train a network to produce a specific output given a specific input. That detail is not important. The main bit here is the memory. You now have a memory unit, except that in Jordan's model, the memory unit has a fixed structure and doesn't really learn how to remember information. All it does is to retain a running average of all past outputs rather than just the immediate past output. And it's used to inform the hidden state computation at each time. So it's a minor extension over the NARX network. And when you train the network, the backpropagation only learns the parameters of the remaining block, the hidden neurons and the output layer. Because this thing has a fixed structure, there is no, and this is the output, there is no gradient that sort of flows back past this memory structure within these networks. A somewhat better model is Elman's model. that also uses a memory unit. But then this memory unit, which Elman calls a context unit, it actually clones okay, so just reading the question. So you're right. So in Jordan's network, this is really not buying you anything very much. Instead of looking at just the recent memory, this guy itself has a running average of all past outputs. So it's some way of summarizing the outputs. That's about it. Whereas if you just looked at only the immediately preceding output, that's a very short-term view of what the network has output in the past. So this was sort of generalizing over that, but then it's not learned. Does that answer your question, Sridhar?
Yeah, thank you.
Right. So in Elman's network, the hidden state now produces the memory. You're no longer referring to the output, except this is cloned. So at each time after you produce the output, you clone this hidden state. And this hidden state now from the previous time feeds in to the hidden state at the current time. And then you make your prediction. Now here, when we train the network, what happens is because you're explicitly just cloning the network, you can think of each column over here as a separate block. And then when you train the network, the backpropagation is going to go down like this, but this is an explicit cloning. There's no real attachment. So the derivatives stop right here. So once the forward computation is performed, for backprop, you literally slice out the net into individual blocks at each time and compute the gradient slope. There is no exploding gradient. There is no gradient flowing backwards. These are what are called simple recurrent networks. So they can be no exploding or vanishing gradients. We haven't even mentioned those yet, right? But here there is no gradient. Gradients never flow beyond this little block. So there is no question of gradients flowing over long periods of stretches of the network and blowing up or shrinking. So here's the story so far. In time series analysis, models must look past inputs along with current input. Look at past inputs along with current inputs. Looking at a finite horizon of past inputs gives us a convolutional network. Looking into the infinite past requires recursion. Now, NARX networks recurs by feeding back the output to the input, and they may feed back a finite horizon of inputs. Simple recurrent networks, like Jordan and Elman networks, maintain memory units. Jordan networks in the Jordan network, the memory unit maintains a running average of past outputs. In Elman networks, the memory unit, which is also called a context unit, clones the hidden state from the previous time. We call these simple or partially recurrent models because during learning, the gradients don't flow all the way back. You only have recurrence in the forward pass. In the backward pass, you have gradients flowing down, but at the memory unit, there's no further flow of gradients backwards. So these are partially recurrent units or simple recurrent units. So we have a pole over here. Let's 10 seconds, guys.
Professor?
Yeah.
Can I ask what do you mean by memory neuron networks? Is it the same?
So, okay, so let me stop the polling right here and I'll explain. So the models that we just saw, which had an explicit variable whose job was to store memory, we're calling those memory neuron networks. The Elman and Jordan networks are memory neuron networks.
Oh, okay.
Right? And they do not have true recurrence because while you have recurrence going forward, there is no recurrence in the back propagation because the back propagation treats each column independently. So the answer to the first question is it's false. But the answer to the second question, by definition, memory neuron networks dedicate neurons specifically to store history. So the first one is false and the second one is true.
So even if, for example, in the Elman network, the memory is like the hidden units values are only copied to the next iteration. Yeah. So does that also count as a neuron, as it doesn't participate in backpropagation?
It's copy. Think of it as a variable, right? At this point, you are calling it. So as far as it's a unit which stores values or computes values. In this case, the computation is performed by cloning. And so from that perspective, it's a neuron in our network, a unit in our network, right?
Okay.
So now, what is the problem with this Elman network? Why is it partially recurrent? It's partially recurrent because no gradient flows backward from here. So what is the next obvious thing to do? How do you fix this? Anyone? How do you fix this?
Make it learnable. Yeah, that one.
These two guys are always the same, right? This one is cloning this. Why do you want to maintain two separate copies? If I merge them and I have a connection directly from here to here, as far as the forward inference is concerned, nothing changes, does it?
Yeah, right.
Right? So I could have just done this instead. And that would also, I mean, I could have had just this arrow and that would do the same job, correct? But now I can propagate my gradients backwards. So is this making sense to you guys?
Yeah, this is making sense. Yeah.
And so that's the next obvious thing to be doing, right? And this, it gives us just a simple modification of the Elman network where you remove the memory unit and make the connection explicit, gives us what is called a state space model. If you're an electrical engineer or if you work on control systems, you're already familiar with this model. Here we define a state variable ht, which holds the internal state of the network at any time t. The state variable itself is computed recursively through the state equation, where ht is some function of the current input and the state at the previous time. And we're going to have to define the initial values to make this work. The output at any time is simply a function of the state. So this is not a discrete machine, right? So we can't be speaking of finite states. These are all continuous valued variables. But it's a state variable in that you have a state variable, which is a real vector, and which is computed recursively, and the output depends on the current state. Now, this is what we'll call a fully recurrent network because this is simply the same as the Elman network, but now with a direct connection from here to here. All that happened is now, if you look at this figure and you compare it with this equation, you're going to see that this h of t is the hidden state, which depends on the current input and the previous hidden state, and the output is simply a function of the hidden state. So this is your simple state space model. This is what it's going to look like. The upper figure shows the actual model. The green portion shows the portion of the network that represents the hidden state. At any time, the hidden state ht is computed from the input at that time and the hidden state at the previous time. The brown box is the output layer of the network, which computes the output from the hidden state. And this lower block shows the entire computation for an input series. So if I have a series of inputs, the total computation is shown here. Every column is just a copy of this figure over here. So every column is identical to every other column. And so at each time, you compute the hidden state from the input at that time and the hidden state at the previous time. For this thing to work, we need one extra term, which is the hidden state at time -1, which is what you'll need to compute the network at time 0. So this is also going to be an extra term, an initialization term that we will need. And now you can follow the arrows. An input at time 0 continues to affect the outputs forever. And so this is an infinite response system. Now,
Professor, I have a question here. So I might have missed this part. But what is the advantage of feeding hidden output compared to the actual output? Initially, we were feeding the output of the entire network to the input, right?
So that is going to be right here, correct?
Okay. Okay.
So here's what. The output is a very compressed version of the hidden state, right? You take the hidden state as a lot of detail, and then you sort of zap it down to obtain maybe a bunch of class probabilities or logics. So the output variable is actually much less informative than the HT itself.
Yeah.
Answer your question?
Yeah, that makes sense. Thank you, sir.
Because although I've drawn the HT with a single box, it doesn't mean HT must be a single layer. HT can actually be a pretty complex thing all by itself with any number of hidden layers. The only requirement is that regardless of the complexity of the state, we need to define HF -1 for that state to enable us to compute the output at the current time instant. So here, for example, is an RNN with a single hidden layer. Now, over here, in this model, the green box represents a single layer. We have to define HF -1 for that one layer. And the figure shows the entire computation for a series of inputs. All columns are identical. Now, here's an RNN with 2 hidden layers. So the hidden state consists of this block with 2 layers. Again, this is a pretty simple model. The input goes into the first hidden layer, and the output of the first hidden layer goes into the second hidden layer, and that goes into the output. But then the first hidden layer also refers back, or the first hidden layer at any time refers back to this same hidden layer at the previous time. The second hidden layer at each time refers back to the second hidden layer at the previous time, which means that we need to define the initial values for both layers when we initialize the network. Now, here's a network with a more complex hidden state with 2 layers. Here again, these 2 green boxes represent the hidden state. So this figure still is in the same spirit as the state space model we defined earlier, except that in the structure of the network, both of the hidden layers are getting, in addition to the inputs that we saw for the previous model, they are getting direct inputs from they are getting values directly from the input as well. So, or you can have something even more complex, right? Like this one. Now the hidden states even have cross connections across time. So these things can get fairly complex. The key bit is that this entire green region is your recurrent hidden state. And the hidden state at any time depends on the hidden state at the previous time and the current input. And now anyone who sees this can immediately say, okay, why only the past input? So the network is not restricted to looking back at only one time instant. The hidden layers can also receive connections from further back, like over here, the hidden layer receives connections from the previous time and from 2 time steps ago. And this is also perfectly valid, right? Now you have a recurrence in the hidden state, which is deeper. And of course, to make this work, you now have to define your initial values for as many previous time instants as the depth of the recurrence. So here, because you have reference going back 2 time instants, at this time, you will need to have, for the second layer, you're going to need to define the initial value at time -1 as well as -2. But this too is just another instance of the state space model that we just saw. And so as you can see, these things can be very complex, but the concept remains the same. And making these models more complex basically means that the output at each time is going to be drawing on more information from previous times. Now, the most popular structures remain these simple ones, fortunately, because it turns out that making the model more complex than this doesn't really buy you a whole lot. And they're also simpler in terms of implementation and computation. So this is the kind of structure we generally have. And again, in every case, it's an infinite response system. An input at any time is going to affect the output forever. Now, often, when we draw these networks, we won't draw the full unrolled figure I've been showing. We'll use simpler structures like these. So the figure will only show one column of the input with little looping connections depicting the recurrence. Here, if you see a figure like this for a recurrent network, an RNN, you should not interpret this loop as saying that the hidden layer feeds back to itself. Actually, what this means is that this hidden layer feeds back to itself at the next time, not at the same time. So if you have a figure of this kind, this is the computation that it actually represents. Or if you have a figure of this kind, where you have 2 hidden layers with recurrence, the actual computation represented by this figure is the one shown in the lower block. Or for this figure, the actual computation is shown by this one here. Again, the point over here is that when you see depictions of this kind, this little loop doesn't mean that there's information going out from the hidden state back into the hidden state at the same time. It means there's a recurrence into the next time. So this loop means that the output of this hidden state at any time feeds into the same hidden state at the next time. So so this is the actual model is going to be an unrolling of the figure. Now that's for depictions, but then let's look at the actual computations of this network. For this simple single hidden layer recurrent network, the ith neuron, you would have initialized the hidden state value at time -1. So the ith neuron in the hidden state at any time is going to operate on an affine function of the input at that time and of the hidden state at the previous time, and also, of course, also a bias. So the hi of t is obtained by applying an activation to a weighted combination of the inputs at that time plus a weighted combination of the hidden states at the previous time plus the bias. And the output, of course, is going to be just an activation function applied to an affine function of the hidden state. So, or let's say, now, so the key piece over here, what are the parameters? If you look at the structure, the hidden state at any time is working on a weighted sum of the inputs. So you have the current weights, the weights that go vertically, plus a weighted sum of the hidden state at the previous time. So you have weights corresponding to this looping edge. So this is the recurrent weights. And so you're going to have current weights from X to the hidden state, recurrent weights from the hidden state to itself, and also current weights going up to the output. If you have, say, this somewhat more complex network, again, the computations are very simple. You would have the initial values for both sets of hidden states defined. The hidden state value for the first hidden layer is going to be obtained by applying an activation function to an affine function of the inputs, the hidden state values themselves at the previous time. So the argument over here is at any time is a weighted sum of the inputs plus a weighted sum of the hidden state at the previous time plus a bias. So again, the parameters are the current weights going up here and the recurrent weights on this edge. We'll talk to Tan about that in the next class, about why tan H is effective. Okay. The second layer is going to be operating on an affine function, which is of the hidden state, first layer hidden states at the same time, and the second layer hidden states at the previous time. So the parameters of the second layer are these current weights and the recurrent weights from the layer itself at the previous time, and of course the bias. And the output, of course, in this model is simply obtained by applying an activation to an affine function of the second hidden state. So we'll get to that as well, right? Just bear with me for the second class. Non-linearity is compressed down. So the job of the non-linearity over here is to help you summarize information. You can't just keep adding things. Things will blow up or disappear. We'll see that this happens. Okay. And I have similar equations for this more complex model, which is, you can make out exactly what the operations are. So for the first hidden state, the parameters are going to be these current weights and these recurrent weights. For the second hidden state, you're going to have the parameters are going to be the current weights from the first hidden layer, the current weights from the input, and the recurrent weights from the second layer itself. For the output layer, the parameters are the weights from the second hidden layer, and from the first hidden layer. So the figure, just every arrow in this figure gives you one set of parameters in the model. So you get an idea, right? In general, though, I'm just going to show the whole thing with a figure of this kind. Now, in the figures that we've seen so far, we've seen one version of a recurrent network where you get a sequence of inputs and you produce a sequence of outputs. Regardless of which model you saw, it was always the case. We can, in fact, have many variants to the structure. So the simplest one is where a single input produces a single independent output. So here there's no recurrence. This is just an MLP. Or you can have a single input producing a sequence of outputs. So this is what we'd have for sequence generation. For example, if you input an image and output a caption, this is the kind of model you would have. Or you could have a series of inputs, and at the end, you have a single output. So this is what you'd have for speech recognition or text classification. You'd see the entire text, and you decide its category. Or we can have delayed sequence-to-sequence models, where the entire input is read, and then an entire sequence of outputs is produced. So this is what we'd have for machine translation. You see the entire English text, and then you produce the entire French text. And then, of course, you can have the regular model that we've been seeing so far, which is a many-to-many model. And each time you get an input and you produce an output. So this is what we did for stock prediction, for instance. Now, it turns out that this model over here is a generalization of all of these other models that we have here. So of 1, 2, 3, 4, 5, all 5 of these models are cases of this guy. And so I'm going to continue to use this model for continue today's discussion using this model because it's representative of all of the other models. And so here's our story so far. Time series analysis must consider past inputs along with current input. Looking into the infinite past requires recursion. NARX networks achieve this by feeding the output to the input. Simple recurrent networks maintain separate memory or context units to retain some information about the past. State space models retain information about the past through recurrent states. So these are fully recurrent networks. Now, state space models, and they have initial values, and these initial values over here, I forgot to mention, these initial values can actually be learnable. So you can figure out, you can learn what is the optimal setting for these initial values. And finally, state space models enable the current error to update parameters in the past. So you have, for example, an error that happens at this time can be backpropagated so that you can actually update parameters out here. So any questions?
I have a question about, can you go back, I think, 2 slides? Yeah, here, in the figure on the left, why does, like, the first 2 columns do not have an output?
So you can have, so this is a structure, this is one case of the model. So let's say this is how you would want to structure the model, right? So let's say you're doing machine translation. Then these will be your English words. These will be your French words. You cannot actually translate word to word, correct? You don't even have a one-to-one correspondence between the English words and the French words. The sentences may be completely different lengths. So in this case, you want to read the entire English text and then produce the entire French text. So that structure would look something like this.
Okay, and when you mentioned the error can be backpropagated over many steps before, I'm not sure I completely understand, because I thought like you evaluate the output at every time step, right? So how do you exactly propagate it back so many time points?
That's what we're going to see next, right?
In the story so far slide, the last point, I think.
Yes, that's exact. So we will see that now. That's exactly what I'm doing.
Okay, sure.
So how do we train these networks? We're going to employ a technique called backpropagation through time, or BPTT. Our training data now consists of input-output pairs where the input is a sequence and the output is also a sequence. So an input will have a sequence of, an X will be a sequence of input vectors, and the desired output is going to be a sequence of outputs. So for example, if you're training a stock market predictor, the input is going to be the sequence of stock value vectors for the past, say, 10 years. And the output is going to be, what predictions you think you should have made on each of those days. So you're going to get a sequence going in and a sequence going out. Every training instance is going to be a pair of sequences. And we want to train this network to minimize the error between the actual output sequence and the desired output sequence. Now, it's important to realize that the unrolled computation over here, I'm showing you the complete computation, is actually one giant neural network. The only difference is that you have shared parameters, in the sense that all of these columns are identical and share parameters. So that means this neural network can be trained via gradient descent or its variations using shared parameter gradient descent rules. To compute the gradients, first we will have a forward pass through the entire network, followed by back propagation to compute gradients. We just have to pool the gradients to account for parameter share. So given a current set of parameters, for each training input for the forward pass, we'll pass the entire sequence of inputs through the network and obtain a sequence of outputs. Now, so here is the pseudocode that you have for this kind of operation. You're going through time. At each time, let's set the initial, the zero hidden state is the same as the input. At each time, you go through the layers of the network. Within each layer, you compute an affine function of the hidden state at the current time from the previous layer, the hidden state from the previous time in the same layer and the bias. And then from this affine value, you compute the hidden state in the current layer at the current time. So once you've gone through all the layers, you're going to compute similarly compute the affine value at the output layer, and then finally the output. The pseudocode is written in vector notation. So all weights and matrices and all multiplications are and additions are matrix vector operations. So now we perform the forward computation. We have to compute gradients, so the gradient descent update rule. And for this, we're going to use backpropagation on individual training instances as before. Now note again that this entire computation is just one giant neural network with shared parameters. So every column here is identical to every other column. Backpropagation requires you to start at the final layer of the network, so which is going to be this guy out here, and perform computations backwards through the network. So we will start at the final time and compute our gradients traveling backwards. This is the reason we call it backpropagation through time. And I'm going to show you how to do this with just one training instance. Also, I'm going to modify the picture slightly. So instead of showing horizontal arrows over here, I'm showing these loopy arrows to show you that the output of this hidden layer is feeding back as input out here. So now, as a first step, we need to compute a divergence between the actual and desired output sequences. Again, the divergence is not computed for individual predictions. This is a sequence model. It's taking in a sequence of inputs. It's making a sequence prediction. So the output is a sequence. The divergence is computed between the output sequence and the desired output sequence. So it's actually explicitly the divergence between two sequences. You could define it as the sum of divergences computed locally at each time, but that's a special case. The most generic case, this is a divergence between an input and actual output sequence and a desired output sequence. Now, you may wonder what the difference is, and it can be quite large. So consider speech recognition, for instance. The system may output a different, this output sequence is going to be a sequence of words. And the system may output a different number of words than the desired output. So you may have an input, and using the current model settings, the network may just say, hello world. And your target output may be hello, how do you do, right? But the network is not going to produce that because it's not yet fully trained. Now, the two sequences are different lengths. You don't have one-to-one correspondence. And so you can't define divergences as, individually assigned divergences. Now, this kind of issue, the fact that the input and output can be different lengths, actually ends up becoming a significant issue for recurrent neural networks, and we'll deal with that in the coming classes. Now, Before I continue, I'm just going to fix some notation. One thing I mentioned, that regardless of the fact that this is a divergence between two sequences, we will assume that you can compute the derivative of the divergence with respect to the individual outputs, because that is going to be required for backprop. So that, and how that is obtained actually ends up being a challenge. We will deal with it in the next class. We're going to backpropagate all of this data. So here is this lecture is going to go a few minutes over, bear with me guys. So here is my notation. I'm going to, our inputs are all of the form xt, right? This is going to be an input. The desired output at any time, as I'm going to be calling this at any time, is assuming that there's a one-to-one correspondence. I'm going to make that assumption. Then if you have a desired output at any time, it will be dt, but more generally, you just have a desired sequence of outputs. Importantly, each neuron, and for my example, I'm just going to assume only one hidden layer, but you can generalize. So at each neuron, you first compute an affine value. So the hidden layer affine values are going to be shown as z superscript 1. The hidden layer value is going to be shown, obtained by applying the activation function on the z. So I'm going to show that using ht. Using this hidden layer value, you're going to compute an affine value out here that I'm showing as z superscript 2. Then you apply the output activation and you get our value here. That's going to be shown as yt. So that's the notation I'm using, okay? Also, I'm going to be representing all the weights uniquely. So this W superscript 1 is the weight corresponding to this current network. W11 is the weight corresponding to this recurrent connection, which goes from the first layer here to the first layer here. W superscript 2 is the weight corresponding to this connection. The 2 means that this is going to the second layer, because in this particular example, there are only 2 layers, right? This is just for illustration, but you can generalize this easily enough. Now, let's begin our computation. As a first step, we're going to compute the divergence between the actual outputs and the desired outputs. Now, we're going to assume that we can compute the derivative of this divergence with respect to each of these outputs. That is a necessity. Although the divergence itself is computed between two sequences, we will be able to figure out how much perturbing any one of these guys a little bit will change the divergence. So we're going to assume that the derivative of the divergence can be computed with respect to each of these outputs. And so, and this, in fact, being able to compute this derivative turns out to be a challenge. And again, we're going to see this in the coming classes. Now, you can have a special case where the divergence is simply the sum of the divergences at individual times, in which case the divergence is going to be just a sum of local divergences. And in that case, the derivative is easily enough computed, but this is not the generic case. Okay? We're not going to make this assumption. All we are going to assume is that it is possible to compute the derivative of the divergence with respect to yt. So in the first step of backprop, we will have computed the divergence. So we're going to get the derivative of the divergence with respect to this final term. And now, once you compute the derivative of the divergence with respect to this final term, which is this guy here, you can compute the derivative with respect to this affine value out here, this term, simply by post-multiplying this derivative, this divergence, with the Jacobian of this activation, which is shown by this function here. So this is just straightforward backprop. This is just like an NLP. So This clear to everybody? If I have the derivative here, I can get the derivative here. Is that making sense to you guys? Yes, no?
Yeah.
This is very straightforward, right? And so now I can compute the derivative with respect to the output over here. All I do is multiply the derivative with respect to the Z2 by the weight matrix for this connection, right? By the weight matrix for this connection. And so that's going to give me the derivative for at this point, the output of the hidden layer. In the process, I can also compute the derivative with respect to these weights, the weights for this connection. And the derivative for these weights is simply going to be obtained by the output of this layer times the derivative at the end of the connection. This is just like an NLP, right? So this equation gives you the derivative with respect to the weights computed out here. So far, we haven't done anything separately from what we do for standard NLPs. And now I can take a step back, and because I have the derivative with respect to this term, I can multiply it by the Jacobian of this activation, and now I get the derivative with respect to the affine combination at the input here, right? So that too is easy, no big deal. And now I can propagate this form down, and I can compute the derivative with respect to this weight, which is going to be the input here times the derivative here. So the derivative with respect to the weight for this connection is the input times the derivative out here. Now this is following the same math that we did for NLPs. You can verify the dimensions and everything will work. But now I can take a step back, and I can compute the derivatives for this weight shown in red. And what is the derivative for this weight going to be? The derivative for this weight is going to be the value out here times the derivative out here, right? So the derivative with respect to the recurrent weight is going to be ht minus 1 times the derivative with respect to z1 of t. Again, straightforward application of NLP rules so far. Nothing fancy, right? So is this clear to everybody? What I got so far?
Yeah, this is clear.
And now, so I'm going a little over, guys, just bear with me, okay? Now I can go back to the previous step, and starting from here, I can backpropagate and compute the derivative out here. I'm assuming that I have the derivative of the divergence with respect to yt minus 1. And so if I multiply that by the Jacobian of this activation function, I'm going to get the derivative with respect to this affine term, right? But then now is the first interesting change. When I want to compute the derivative with respect to the output here, this output was passed here as well as came out here, right? So the output actually took two paths going out. So the derivative of the divergence with respect to ht minus 1 is going to have two components. One which comes straight down, which is the derivative with respect to the affine value over here, z2, times the weight for this connection. And the second one is going to be the derivative out here, which is this one, times the weight for this connection. So is this equation making sense to you guys? Yes, no?
So is it like the gradient from that particular loss, let's say y of t minus 1, added with that from the hidden layer from y of t? Is it?
Yeah, basically It's going to be this derivative coming down plus this derivative, right?
Yeah. This makes sense.
So this term, this first term, is the derivative coming down this way. The second term is the derivative coming down. This way. Okay. So and now, of course, I can come. So here's the second change. Now I can compute the derivative for the weights of this connection, and that derivative is going to be this output times the derivative out here, right? So that's going to be ht minus 1 times the derivative of the divergence with respect to z2 at t minus 1. But then observe, these columns are all identical, right? So this weight is the same as this weight. And we've already computed a derivative for that weight at this time. So using shared parameter rules, the derivative that you compute here is actually going to be added to the derivative you computed previously. So to compute the derivative for this weight, you compute the local derivative out here, which is ht minus 1 times the derivative with respect to z2t, and then add z2t minus 1, and then add that to the derivative you computed at the previous time. So is this making sense to you guys? Why we make that, we have the addition? Is making sense, guys?
Yeah.
And now we can use the standard gradient descent rules. I mean, the chain rule. From the derivative here, you can compute the derivative here by post multiplying by the Jacobian. But then once again, now when I compute the derivative with respect to this weight, that's going to be xt minus 1 times the derivative here, the derivative with respect to z1 and t minus 1. But then because these weights and these weights are identical, this derivative is actually going to get added to the derivative you computed out here. So the derivative with respect to the weights for this connection is going to be the sum of the derivative computed here and here. So this is going to get added, incremented. And then you can move your way back and compute the derivative with respect to these weights. But then again, as before, the derivative with respect to these weights is going to be the product of the value here and the derivative here. And that's actually going to be added to the value that you computed from the previous connection. So this is an increment. And so now you can keep following that logic all the way back. And eventually when you get to the end, you can also compute the derivative with respect to hf minus 1 and compute and obtain that value as well. So here is the complete set of derivatives. Initialize all derivatives to 0, and then go back in time and compute derivatives for all intermediate variables. And the most important thing is that the derivatives for the weights are always incremented because you're using the fact that all of these guys have the same parameters. So when you compute the derivative out here, you're going to add it to what you already have from other times. So and then finally compute the derivative with the initial state value. So I have I was supposed to have a whole here. I'll skip that. I have pseudocode over here for BPTT. This is just sort of literally just implements the procedure that I just showed. I'll stop here and I'll stop the recording as well. Oh my good God. I forgot to record this lecture.